Hello everyone, welcome back. In this video, we're going to talk about using the methods that we learned in this chapter and apply them to situations where we want to find the most optimal outcome. Now, these types of applications are called optimization problems. For example, a businessman wants to minimize the amount of costs to run a business and to maximize its profits. A farmer may want to maximize the amount of area that they can enclose with a fixed amount of fencing, and manufacturers may want to minimize the amount of waste material produced. Now, the general idea behind optimization problems is that we're looking for an absolute minimum or absolute maximum of a function. And we know that if we're given a closed interval for our function, then if the function is continuous, it will have to achieve an absolute maximum and an absolute minimum somewhere inside that interval. So we can use the closed interval method if our function is defined on a closed interval from a to b. Now, if the function is defined on an open or infinite interval, but there is only one critical number of our function, then we can use the first derivative test to determine the absolute extrema in that case. So here we have a modified version of the first derivative test where we only have a single critical value. So this is called the first derivative test for absolute extreme values. So suppose that c is a critical number of a continuous function defined on an interval. So we know that if the sign of the first derivative is positive for all values of x that's less than this critical number, and then it's negative for all values of x greater than this critical number, then f of c is going to be the absolute maximum of f. If the derivative is negative for all values of x less than c, and then it's positive for all values of x greater than c, then f of c is the absolute minimum. So here is a problem-solving strategy for tackling optimization problems. And we'll go through these steps in the following examples. So let's have a look at the first example. So suppose a farmer has 2,400 meters of fencing and wants to fence off a rectangular field. So in part A, what are the dimensions of the field that has the largest area? Now, if you recall from geometry, if you consider all possible rectangles with the same perimeter, then the one that has the largest area is going to be a square. And we're going to prove this by using calculus. So let's first draw a diagram of our situation. So here we want to fence off a rectangular field. So let's call the dimensions of the fence as L and W, so the length and the width of the field. And we're given that the farmer has 2,400 meters of fencing. And so what this tells us is that the perimeter of the fence, which is the sum of all of the sides, is going to be 2L plus 2W. And this has to be equal to 2,400 meters. And so this gives us a constraint on the amount of fencing that we can use. And now what we want to look for is the dimensions of the field that gives us the largest area. So in other words, we want to maximize the area of the fence or of the field. So now if we write the area of the field, which is going to be the length times the width, then this is our function that we want to find the absolute maximum. So now if we look at this function, we have two variables. What we need to do is eliminate all but one of these variables. And it doesn't matter which variable we eliminate. So the way that we can eliminate one of the variables is by using our constraint. We know that the perimeter has to be 2400 meters. And we're also given that the perimeter is 2 times the length plus 2 times the width, which needs to add up to 2400. So we can use this equation and solve for one of these variables. And this will allow us to eliminate one of the variables in the area function. So let's solve for W. So 2W is going to be 2400 minus 2L. And dividing by 2, we get that W is 1200 minus L. So now we can substitute this into the area function. So the area is the length times 1200 minus L. And now the area is going to be a function of the length of the field. So it's only a function of one variable. And because we want to find the absolute max and min, we will simplify our area function by distributing. So that is 1200L minus L squared. So this is the function that we want to find the absolute maximum for. So now we'll also need to consider the domain of this function. So recall that L is the length of the field. And since distances can't be negative, the smallest value of L that can be used is going to be 0. Now, what is the largest value of L that we can use? So we know that L is going to be the length of one of the sides of the field. And we are restricted to 2400 meters of fencing. And because there are two sides that have a length of L, then the largest length that L can be will be half of the perimeter. So if the length of L is equal to 1200, then that is the most amount of fencing that we can use so that we still make a rectangular field. So the domain of this function is going to be from 0 to 1200, including the endpoints. So here we have a closed interval, and our function 1200L minus L squared is continuous on this domain. So we can use the closed interval method to determine the absolute maximum of this function. So using the closed interval methods, the first thing we'll look for are the critical numbers. And to find the critical numbers, we need the first derivative. So A prime is going to be 1200 minus 2L. And then we'll set the first derivative equal to 0, and then solve for L. So that gives us 1200 minus 2L equals 0. So that is 2L is equal to 1200. So L is 600 meters. Now, since the derivative is a polynomial, it is never undefined. And so that tells us that 600 is our critical number. And the next step is to evaluate our function at this critical number. So the area of the fence when the length is 600 meters is going to be 600 times 1200 minus 600. So here we're substituting 600 for L into the area function, and we end up with 600, oops, times 600, which is 360,000 square meters. So now we will evaluate the area function at the endpoints. So what is the area of the fence, or of the field, when the length is 0 meters? Well, we have 0 times 1200 minus 0, which is 0 square meters. And then what is the area when the length is 1200 meters? Well, that's 1200 times 1200 minus 1200, which is also 0 square meters. And if we compare all of these values and choose the largest among them, then that will give us the absolute maximum. So the absolute maximum occurs when the length is 600 meters. So now that we have the length of the fence, we can also determine the width. We know that the width is 1200 minus the length, and that is from our perimeter equation. And so we have that the width is 1200 minus 600, which gives us 600 meters. And so these are the dimensions of the field that gives us the largest area. So the dimensions of the field with the largest area is 600 by 600 meters, which is a square. Now in part B, suppose that the farmer once again wants to fence off a rectangular field that borders a straight river, but does not need fencing along the river. So what are the dimensions of the field that has the largest area in this case? So here we have a river, and we have a rectangular field, and we'll call the sides of the rectangle as L, and then the horizontal distance as W. So once again, the farmer has 2,400 meters of fencing. Now the only thing that changes from the previous problem is that the perimeter is going to be 2L plus W rather than 2L plus 2W. So this has to be 2,400 meters. And again, we want to maximize the area function. The area of the rectangle is still length times width. But now if we solve for, let's say, the width from the perimeter equation, we have 2L plus W is 2400. So W is 2400 minus L, 2L. And so now the area function is going to be L times 2400 minus 2L. So now the area is only a function of its length, which is 2400L minus 2L squared. Now let's consider the domain of this function. So L is the length of the sides of the rectangle. Since distances can't be negative, we know that it has to start at 0. And again, the largest value that the length can be is going to be half of the perimeter because there are two sides of length L. So if the length of the sides is 1200, then that is the maximum amount that the length can be. And so our domain is, once again, the closed interval from 0 to 1200. Now, if we considered solving for L in the perimeter equation instead of W, then we would end up with L is 1200 minus W over 2, in which case the area function is going to be 1200 minus W over 2 times W, which can be simplified to 1200 W minus W squared over 2. Now, as a function of W, the domain of this function will be different from the domain of the other function. So W represents the width of the rectangle. And for this domain, the smallest value is going to be 0, since distances can't be negative. But the largest value is going to be 2400, since there's only one side of length W. So now let's use the closed interval method to determine the absolute maximum of this function. So let's find a prime of L. So that is 2400 minus 4L. The critical numbers can be found if we set the derivative equal to 0 and then solve for L. So we have 2400 minus 4L equals 0. So 4L equals 2400. So that it gives us that L is 600. And again, the units are measured in meters. Now we'll also evaluate the area function at the critical number. So the area, when the length is 600 meters, is going to be 600 times 2400 minus 2 times 600. So that is 600 times 1200, which gives us 720,000 square meters. So now let's evaluate the area function at the endpoints as well. So what is the area when the length is 0 meters? Well, that's 0 times 2400 minus 2 times 0, which gives us 0 square meters. And what is the area when the length is 1200. That gives us 1200 minus 2400 minus 2 times 1200. And this will give us 0 square meters. And now comparing all of these values and choosing the largest among them, we see that the absolute maximum occurs when the length is 600 meters. So now that we have the length, we can determine the width from the perimeter equation. The width is 2400 minus 2 times L. So that's 2400 minus 2 times 600, which gives us 1200 meters. And so the dimensions of the fence that it gives us the largest area is going to be 600 meters by 1200 meters. Now in the second example, we have a cylindrical can that is to be made to hold 1 liter of oil. So what are the dimensions that will minimize the cost of the metal to manufacture the can? So now to minimize the cost of the metal to manufacture the can, we want to minimize its surface area. So let's first draw a diagram of our situation. So here we have a cylindrical can. Here I'm going to use a bit of color. And let's call h to be the height of the can, and r is going to be the radius of the can. So we know that the volume of the can is going to be 1 liter. And to find the volume of the can, we take the area of the base multiplied by the height. Now the base is going to be a circle of radius r, and so the area of the base is going to be pi r squared. And then to find the volume, we will multiply this by the height. And so the volume is going to be pi r squared h, and this has to be 1 liter. And since we want this to be in measurements that we want to use, we can convert this into cubic centimeters. So 1 liter is equivalent to 1,000 cubic centimeters. So that is our constraint of this can. And so now what we want to write down is the surface area of the can. So the surface area of the can is composed of the top and the bottom of the can, which are circles. And if you imagine cutting up the side of the can and then laying the can flat, then we should see a rectangle. Okay, so if you were to cut the can and then lay the side of the can flat, what we observe is going to be a rectangle. The sides of the rectangle is going to be the height of the can. Now the width of the rectangle is going to be the circumference of the circle. And the circumference of the circle is going to be 2 pi r. So now we can write down the surface area of the can. So let's let S be its surface area. And it will be equal to 2 times the area of the circle plus the area of the rectangle. So the area of the circle is going to be pi r squared. So we have 2 times pi r squared plus the area of the rectangle, so the side of the can, which is 2 pi r times h. And so we want to find the minimum of this function. Now notice that we have two different variables in this equation. We have both r and h, and so we need to eliminate one of these variables. So it's easiest if we look at eliminating the h variable from this equation. So from our constraint, we know that the volume has to be 1,000 cubic centimeters. So we're given that pi r squared times h has to be equal to 8,000. So we can solve for h in this equation and then substitute it into the surface area equation. So dividing by pi r squared, we get that h is 1,000 over pi r squared. So now we can write the surface area as 2 pi r squared plus 2 pi r times 1,000 over pi r squared. So now the surface area is only a function of r, the radius of the can. So now let's simplify. We have 2 pi r squared. We know that the pi's can cancel, and one of the r's will cancel, which gives us plus 2,000 over r. And since we want to find derivatives eventually, let's rewrite it as a negative power. We have 2 pi r squared plus 2,000 r to the negative 1. So this is our function that we want to find its absolute minimum. Now let's consider the domain of this function. So r is the radius of the can. And since it is the radius of the can, it can't be a negative value. So it has to at least start from 0. Now if we look at our function, the radius can't be 0 because it would be undefined at 0. We have 2,000 divided by r, and r cannot be 0. So the domain is going to be the open interval from 0. Now, we aren't given any restriction to the amount of material that we can use. And so the radius can be any radius that we like. And so our domain is from 0 to infinity. Okay, so the function s is undefined at 0. So we will exclude 0 from our domain. And we are not given a restriction on the material. And so the radius can be as large as we like. And so our domain is from 0 to infinity. So now because we're not given a closed interval, then we can't use the closed interval method for finding the absolute minimum. And so we're going to look at using the first derivative test. And hope that there is only one critical number for this function. So let's calculate the derivative. So s prime of r, which is 4 pi r minus 2000 r to the negative 2. So now we can rewrite this as 4 pi r minus 2000 over r squared. We'll make a common denominator of r squared. So multiplying the 4 pi r by r squared over r squared, we get 4 pi r cubed over r squared minus 2000 over r squared. So we have 4 pi r cubed minus 2000 all over r cubed. And we can factor a 4, leaving us with pi r cubed minus 500 all over r cubed. So that is our first derivative. So now let's look for the critical numbers. So we'll set the derivative equal to 0 and then solve for r. And so the derivative is 0 if the numerator is equal to 0. So that gives us 4 pi r cubed minus 500 equals 0. We divide both sides by 4. And then solving for r, we get pi r cubed is 500. R cubed is 500 over pi. And so r is the cubed root of 500 over pi. And we are measuring in centimeters. So let's also consider the case when the derivative is undefined. The derivative is undefined if the denominator is equal to 0. So if r squared equals 0, then the derivative is undefined. Solving for r, we get 0 as our value. Now 0 is not in the domain of S. And so we will not consider this to be a critical number. And so this tells us that the only critical number for this function occurs at the cubed root of 500 over pi. So now the only thing that is left to show is that we have an absolute minimum. And so we'll use the first derivative test and look at the sign of the first derivative near this critical number. So our domain is from 0 to infinity. So we're looking for the sign of the first derivative. So let's test a number between 0 and the cubed root of 500 over pi. So for example, we can look at choosing the cubed root of 400 over pi. So if we substitute this into the first derivative, we get 4 times pi, the cubed root of 400 over pi cubed minus 500 all over the cubed root of 400 over pi squared. So this gives us 4 times pi. The cubed root and the cubed will cancel, so that is 400 over pi minus 500 all over the cube root of 400 over pi squared. And simplifying, we get 4 times 400 minus 500. And this will give us negative 400 over the cube root of 500 over pi squared. So we know that this is a negative number, which means the function is going to be decreasing on this interval. So now let's test the first derivative, for the sign of a number greater than the cube root of 500 over pi. For example, we can choose the cube root of 600 over pi. And substituting this into the first derivative, we get 4 times pi, the cube root of 600 over pi cubed minus 500 all over the cube root of 600 over pi squared. And if you perform the same calculations or simplifications as before, we will end up with positive 400 over the cube root of 600 over pi squared, which is going to be a positive number. And so this tells us that the function is increasing from the cubed root of 500 over pi to infinity. So using the first derivative test, we know that the cubed root of 500 over pi is an absolute minimum. And so the absolute minimum occurs when the radius is the cube root of 500 over pi centimeters. So now we can also determine the height of the can from the volume equation. We know that the height is 1,000 over pi r squared. So 1,000 over pi times the cubed root of 500 over pi squared. And this is also measured in centimeters. And so the dimensions of the can that minimizes the cost of the metal is a radius, which is the cube root of 500 over pi centimeters, and its height of 1,000 over pi times the cube root of 500 over pi squared centimeters. So we'll go through the remaining examples in the lab. So I encourage you to try these examples and we'll cover them in the lab period. So I'll see you all then.